In 1950, Alan Turing, the father of computer science, asked a question that would change the world. Can machines think? This question marked the beginning of an era of artificial intelligence, an era in which humanity strives to create machines capable of mimicking or even surpassing our intellect. The first significant step on this path was the Chess Player project, when in 1951, the first computer program capable of playing chess was created. 5 years later, at the Dartmouth Conference, a group of scientists officially announced the birth of the field of artificial intelligence, defining it as the science and technology of creating intelligent machines. Decades of experiments and discoveries followed. In 1997, the world was astonished when IBM's supercomputer Deep Blue defeated the world chess champion Garry Kasparov. This was the moment when AI first surpassed a human in one of the most intellectual games. In 2011, an IBM computer named Watson reached a significant milestone. It did what was considered impossible by defeating 2 human opponents in the game show Jeopardy! Millions of viewers who witnessed this event saw Watson demonstrate an amazing ability to process and analyze information, methodically defeating its opponents. Answering complex questions that baffled his rivals, it won and claimed a $1 million prize. With a processing power of 500 gigabytes per second and 16 terabytes of RAM, along with access to 200 million pages of various reference materials, including the entire Wikipedia, Watson became a symbol of the capabilities of modern computing systems. Watson is part of the development of expert systems, programs that use formal logic to work with large amounts of data. A recent example includes medical expert systems, AI doctors capable of consulting you on medical issues with 99% accuracy directly on your smartphone. You describe your symptoms. The system searches databases of leading world medical centers and gathers the latest scientific information. After this, it gives you personalized recommendations, taking into account your specific characteristics. Similarly, there are now lawyer robots and secretary robots that facilitate routine tasks and personal organization. Yes, even robotic dogs have appeared. Moreover, chatbots based on large language models have been developed, capable of passing business school final exams, generating computer code, and writing poetry. In 2023, a significant portion of computer code was written using artificial intelligence tools, especially using Copilot. According to GitHub, artificial intelligence already generates about 40% of the code among developers using Copilot. It is expected that within 5 years, Copilot will be able to write up to 80% of the code. After Watson's victory on the game show, some analysts expressed concerns about the day when machines will surpass humans. Meanwhile, Ken Jennings, who lost to the computer, jokingly welcomed our new computer overlords in a conversation with the press.
And I, for one, welcome our new insect overlords.
The question arises, if Watson was able to defeat experienced and seasoned show professionals in a face-to-face competition, what chances do we mere mortals have against machines? Jennings joked that he and the other show participant, Brad, became the first knowledge industry workers to lose their jobs at the mercy of the new generation of thinking machines. However, while welcoming thinking machines, people sometimes forget that you cannot approach a computer and congratulate it on a victory. It's impossible to pat it on the back or share a drink with it. It does not understand what that means. Moreover, Watson was not even aware that it won. If we set aside the fantasies of sensation-hungry journalists and involuntary anthropomorphism, it turns out that Watson is a complex calculating machine, capable of searching data and performing calculations billions of times faster than the human brain, and it completely lacks self-awareness and common sense. The development of artificial intelligence is impressive in terms of computational power, yet the creation of autonomously thinking machines has not yet been achieved. Considering Moore's law, which states that computational capabilities have doubled every 2 years for the last 50 years, some speculate that machines will eventually achieve self-awareness, necessitating human readiness for this moment and having a significant impact on the future of civilization. For example, renowned inventor and futurist Ray Kurzweil, an expert in artificial intelligence, predicts the emergence of AGI, artificial general intelligence, by 2029. If you're thinking, who is he, or what naive optimism is this? Here's a quote. Among the people I know, Ray Kurzweil is the best at predicting the future of artificial intelligence. Bill Gates. Since the 1970s, Kurzweil has been involved in pattern recognition, machine learning, and the design of artificial intelligence. He created the first music synthesizer, the first flatbed scanner, and the first reading machine for the blind, and was the first to teach computers to recognize human speech. These are just some of his personal achievements, not to mention his work with Google, IBM, and founding successful companies. Ray has written a series of books about the future of technology, including a book predicting the singularity. The technological singularity is a state of the world where technological progress reaches a point beyond which it becomes uncontrollable and irreversible. Machine intelligence merges with human intelligence, leading to radical changes in the life of civilization. According to a popular theory proposed by mathematician and cosmologist Irving Good, known as the intelligence explosion, a self-improving intelligent agent could ultimately trigger a runaway reaction of self-improvement cycles, whereby each new generation of AI appears faster, causing a sort of intelligence explosion, and ultimately creating a superintelligence far surpassing all of human intelligence. Years ago, Kurzweil predicted that the singularity would be reached by 2045. Many debated this and predicted much later dates, but now predictions have changed. Kurzweil believes that by 2029, a computer will be able to pass the Turing test, a test where, in a 30-minute interaction, a human cannot tell whether they are communicating with a computer or another human. Kurzweil asserts that after 2029, even a multi-hour test would not reveal to a human that they are interacting with a computer. He does not believe that we should fear technological advancement. According to him, public fear of AI and robots is a product of news that focuses on clickability and emphasizes conflicts, crises, and problems, ignoring positive long-term trends. This results in distorted perceptions of many things, including progress. For instance, surveys show that 70% of people believe that inequality in the world has significantly increased over the past 50 years. However, in reality, inequity and poverty have greatly decreased compared to 50 years ago. The same goes for life expectancy, health, and overall human agency in managing their lives. All this has occurred alongside technological development. Ray Kurzweil is one of the most influential scientists in shaping my philosophy of life. There is a wonderful, deeply optimistic podcast with Lex Friedman on YouTube. I highly recommend it to anyone interested in the future and who envisions humanity's fate in creating a vast diversity of versions of ourselves, from nanobots to galactic-scale intelligences. This video is inspired by Ray Kurzweil's book, How to Create a Mind, and theoretical physicist and MIT professor Max Tegmark's book, Life 3.0. By the way, reading these books will give you more pleasure than watching this video. I'm Sasha, and this is Homo Deus. Predicting the development of artificial intelligence, AI, is challenging because it has already gone through at least 3 phases of highs and lows. In its early days, the 1950s, there was a belief that robotic servants and bartenders would soon appear. Scientists and engineers created devices capable of playing checkers and solving mathematical problems, as well as manipulators for lifting objects. At Stanford University, a robot named Shaky was developed, equipped with a wheeled cart and camera capable of moving independently and avoiding obstacles. Soon, scientific journals began publishing articles filled with enthusiasm, predicting the imminent arrival of companion robots. Some forecasts were quite modest. For example, in 1949, Popular Mechanics predicted that computers in the future would weigh no more than 1.5 tons. Others were extremely optimistic, announcing the imminent arrival of the robot era. Shaky was expected to perform household tasks such as vacuuming carpets and opening doors. It was also predicted that robots would manage spacecraft and communicate with astronauts, as depicted in Stanley Kubrick's film 2001: A Space Odyssey. In 1965, Herbert Simon, one of the founders of artificial intelligence theory, claimed that within 20 years, machines will be able to do everything that a human can do. Dr. Marvin Minsky, another founding father of AI, expressed the opinion that, within the lifetime of this generation, the problem of creating artificial intelligence will be largely solved. However, the 1970s brought disappointment. Computers that played checkers couldn't do anything else, and robots struggled to move around rooms. Shaky easily got lost in unfamiliar surroundings, and scientists were unable to come close to understanding consciousness. In 1974, AI funding in the USA and the UK was significantly reduced. In the 1980s, thanks to the growth in computing power, interest in AI rose again, especially in military circles, hoping to create soldier robots. In 1985, funding for AI development reached $1 billion a year, with hundreds of millions of dollars spent on projects like Smart Truck, creating smart autonomous carts capable of penetrating enemy lines, conducting reconnaissance and independently completing missions, and then returning to their territory. Unfortunately, the only thing they learned to do well was get lost. The blatant failures of such costly and ineffective projects caused another wave of cooling interest in artificial intelligence in the 1990s. Mathematician Paul Abrams, recalling his education at the Massachusetts Institute of Technology, said, "It was as if a group of people proposed to build a tower to the moon. Each time they proudly point out how much higher their tower has become compared to last year. The only problem is that the moon isn't getting any closer." Nonetheless, with the increase in computing powers, a new renaissance of AI has begun. Max Tegmark, in his book Life 3.0, describes his participation in a symposium organized by the Nobel Foundation, dedicated to the topic of artificial intelligence. The discussion among invited experts about the definition of intelligence led to prolonged debates and the inability to reach a consensus. It turned out that even among prominent minds, there was no unity of views regarding the subject of their study, intelligence. This means there simply isn't one correct definition of intelligence. Instead, there exists a rather lengthy list of competing definitions, such as logical thinking, perception, planning, creativity, self-awareness, problem-solving ability, and learning capacity. In the context of this video, we adopt a broad and adaptable definition, not limited to existing forms of intelligence. Intelligence is the ability to achieve complex goals. This definition encompasses all the aforementioned competing definitions. It also includes the definition given by the Oxford Dictionary, the ability to acquire and apply knowledge and skills, as acquiring and applying knowledge are also goals. Given that goals can be very diverse, there are many types of intelligence. Therefore, it is incorrect to evaluate the intelligence of a person, animal, or machine with a single numerical value, such as IQ. Comparing computer programs specialized in playing chess or Go, for example, is not feasible in terms of their skills because each is unique and designed for a specific narrow task. However, we can consider one program smarter than the others if it is at least as good as they are in solving any task and definitely better than them in solving at least some tasks, like beating them in Tetris. Debates over the superiority of one intelligence over another in borderline cases are not very meaningful since intelligence manifests across the spectrum of tasks and does not fit into an all-or-nothing categorization. Max Tegmark writes, "Who has the ability to achieve goals in speaking? Newborns? No. How about radios? Yes. What about a baby who knows 10 words, 500 words? Where do you draw the line?" I intentionally use the vague word complex because it is less interesting to figure out where to draw the line between sensible and nonsensical, and more useful to simply learn to measure the degree of ability to achieve goals for various types of tasks. In such a classification of intelligence, it is useful to distinguish between narrow, weak, and broad, strong intelligence. IBM's chess computer Deep Blue, which dethroned world champion Garry Kasparov, was adapted to achieve a goal within a narrow task area, while, for example, large language model technologies like ChatGPT and Gemini demonstrate successes across a broader spectrum. Human intelligence is unique in its ability to master a wide range of skills and knowledge. A healthy child can successfully learn almost anything in the world. In terms of the breadth of tasks that a human brain can perform, it has no equal, although machines have already surpassed us in some specialized areas. The task of AI research is to create universal or strong AI, capable of achieving any goals, including teaching itself. While the term intelligence may be perceived with a positive connotation, it is important to understand that scientists and engineers use it in a completely neutral sense, referring only to the ability to achieve a specific goal, regardless of whether we consider that goal beneficial or harmful. Similarly with people, one intelligent person may be very good at helping people, another at causing harm. Suppose your future robot assistant has no personal goals, but is ready to fulfill any request you make. If you ask it to prepare an Italian dinner, it will find recipes online, buy the ingredients, and cook you a great meal. You would call that intelligent, although the goal was initially set by you. The robot took your goal and incorporated it into its list of sub-goals, from paying for purchases to slicing Parmesan. Thus, intelligent behavior is always associated with having goals. We humans tend to assess the complexity of tasks based on how difficult they are for us, which can create a distorted view of how complex these tasks are for a computer. For instance, multiplying large numbers might seem more difficult than recognizing a face in a photo. Though computers have long surpassed us in math, while only recently mastering human-level face recognition. This phenomenon, known as Moravec's paradox, is due to the fact that a large part of our brain is efficiently engaging in solving tasks that seem simple to us but require significant computational resources. Canadian engineer and roboticist Hans Moravec uses the metaphor of the landscape of human skills to illustrate this phenomenon. Computers are universal machines, and their potential universally covers an infinite variety of tasks. Human potential, on the other hand, is concentrated in areas where success is crucial for survival, and they are quite weak in more remote areas. Imagine a landscape of human competencies, where there are valleys such as arithmetic and mechanical memory, hills such as chess and proving theorems, and mountain peaks marked with signs like moving from place to place, coordination of hand and eye movements, social interaction. As computers improve, this landscape seems to fill with water. Half a century ago, it flooded the valleys, washing out accountants and scribes, but leaving us dry. Now the water has reached the hills, and the inhabitants of our outposts are worried. Where should they move? We feel safe on our peaks, but considering the rate at which the water is rising, it will cover the peaks in the next half century. I suppose it's time for us to start building arks and get used to living afloat. Since the creation of this concept, the water level has been rising, confirming the forecast. Thus, areas previously considered complex, such as chess, have long been underwater. As the water level rises, there may come a moment when a critical point is reached, heralding radical changes. This moment occurs when machines begin to independently engage in AI development. Until this point, progress is controlled by human efforts to improve computers, but afterward, machines begin to improve themselves faster than humans can, leading to an even more rapid reduction in land. This is precisely the controversial yet fascinating concept of technical singularity. As is well known, Alan Turing proved that a computer capable of performing basic operations and having enough time and memory could be programmed to perform any tasks. Machines surpassing this threshold are called universal Turing machines. In this sense, your smartphone or laptop is a universal computer. Similarly, the intelligence required to create AI is universal intelligence, because with sufficient resources, it can achieve any goal that in principle be achieved by any intelligent entity. This means that if a machine needs to improve its social skills, forecasting abilities, or capacity to develop AI, it will do so. If it needs to build a robot factory, it will build one. Thus, universal intelligence has the potential to become Life 3.0. In the context of Max Tegmark's book, this concept describes life at a new evolutionary stage. Life 1.0 encompasses biological forms that evolved through natural selection with innate abilities that they cannot change during their lifetimes. These organisms are incapable of learning or adapting based on experience to the same extent as higher forms of life. Examples include single-celled organisms such as bacteria and amoebas, which reproduce and adapt at the genetic level through mutations and natural selection, but do not possess the ability to learn during their lives. This also includes plants such as trees, flowers, and mosses, adapting to their environment through genetic changes between generations. It also includes simple multicellular animals such as hydras and jellyfish, responding to the environment with simple reflexes and instincts. Additionally, examples are sponges and corals that form complex colonies without a centralized nervous system, and some insects with limited learning ability, for instance, ants and bees. Life 2.0 describes beings such as humans, capable of learning and adapting to their environment, altering their behavior and knowledge through learning and cultural inheritance. This is achieved thanks to a complex nervous system and brain, allowing these beings to learn from experience and transmit knowledge through teaching, not just through genes. In addition to humans, examples include higher animals, such as elephants, that learn social interactions and have complex forms of communication. Primates, including monkeys, are also capable of learning, using tools, and passing knowledge within the group. Dolphins, whales, parrots, and corvids also demonstrate higher levels of social behavior, learning, and problem-solving abilities. Life 3.0, in turn, opens a new chapter in the history of life. This is the era of artificial intelligence, capable not only of learning and adapting to new conditions, but also of developing independently, transforming its physical and cognitive structures. These entities will be able to independently design and create new versions of themselves and other AIs, possessing the ability to self-improve beyond human capabilities. Just as the father of modern computing, Alan Turing, showed that a universal computer could perform any computations, the concept of Life 3.0 implies that universal intelligence can achieve any goals that can be set or reached. Thus, if such intelligence faces the task of improving its skills in any area, be it social interaction, scientific research, or technical design, it will find a way to do so. If achieving a goal requires creating an entire AI ecosystem or a factory of self-replicating von Neumann probes, Life 3.0 will take it on. AI experts agree that intelligence is ultimately defined by information and computation, not material substances like blood or carbon. Therefore, there are no fundamental barriers to machines surpassing humans. However, what is information and computation in the context of fundamental physics, which asserts that the world consists of energy? How can such abstract and immaterial concepts as information and computation manifest in a material world? In particular, how can elementary particles, following the laws of physics, demonstrate behavior that we call intelligent? When we say that an atlas contains information about the world, we imply a specific connection between the arrangement of molecules in the book that give color to the text and illustrations and the distribution of continents on the planet. If the continents were arranged differently, the molecules of the dyes in the book would have to occupy a different position. Humanity uses many ways to store information, from clay tablets to computer hard drives. All these methods share one important property. The state of these devices is somehow connected to the state of the world objects that interest us, allowing us to retrieve information about these objects. The main property of all these information storage mediums is their ability to maintain a large number of different stable states over a long period, which makes it possible to extract and use the encoded data. For example, consider a landscape with 16 depressions separated from each other and a small ball. If the ball ends up in one of these depressions, it corresponds to one of the 16 possible states. And since the ball can remain there for a long time, its location can serve to encode one of the 16 numbers, from 1 to 16. Such a memory device is quite reliable, as external influences are unlikely to dislodge the ball from the depression, allowing the stored number to be known at any moment. This stability is explained by the fact that moving the ball out of its niche requires more effort than can be exerted by random external influences. Similar principles can be implemented in more complex systems, where the stability of the system state is conditioned by its mechanical, chemical, electrical, and magnetic characteristics. For this reason, solids have many stable states, unlike liquids and gases. For example, engraving on a watch will last many years, as changing the shape of the metal requires a significant amount of energy, whereas a letter O created from smoke will disappear after a second due to the ease of changing the molecular order in the gas. Memory devices are efficient when they have many stable states for encoding information. For instance, the ball on the left can encode 4 bits of information corresponding to one of the 16 depressions. Similarly, 4 bits can be stored together by 4 balls on the right, 1 bit per ball. The simplest memory device has only 2 stable states and can encode 1 bit of information, either 0 or 1. A more complex device is capable of storing 4 bits of information in 16 different states, having the same memory capacity as a system with 16 states. Bits function as certain atoms of information, that is, the smallest and indivisible elements that can be combined to represent any amount of data. For example, typing the word "word" on a keyboard, a laptop converts it into a series of 4 3-digit numbers, encoding each letter as 8 bits, and the color of each pixel on the screen can be defined by 32 bits. Since systems with 2 states are easier to produce and manage, most modern computers use bits to store information, despite the variety of ways they can be physically implemented. On a DVD, each bit is represented by the presence or absence of a small indentation on the plastic surface. In hard drives, bits correspond to different directions of the magnetic field in a certain section. In a laptop's RAM, each bit is reflected by a specific state of electrons in microcapacitors, indicating the presence or absence of a charge. Transmitted bits can move very fast, sometimes reaching the speed of light, as in the case of fiber optic cables, where bits are transmitted through changes in laser light intensity. Engineers strive to create systems that not only ensure the reliability of storage and ease of reading information, as in the case of engraving on a watch, but also the convenience of recording information, requiring less energy expenditure than, for example, metal engraving. It is important for these systems to be easy to handle and economically feasible for mass production. However, the specific physical medium of the bit is absolutely irrelevant to both engineers and users, as the focus is not on the material of the carrier, but the information it stores. When you email a document to a friend to print it out, the information is sequentially copied from one physical state to another, from the magnetic dipoles of the hard drive to the electrical charges in RAM, then to Wi-Fi radio waves, through fluctuating voltage in your router circuits, then to laser pulses in the fiber optic, and finally to molecular charges on the surface of the paper. Thus, information exists independently of its physical carrier, demonstrating its unique ability to transform without loss of content, regardless of its physical substrate. Recognizing the fundamental independence of information from its physical carrier allows engineers to continually improve data storage devices using the latest technologies, without the need to change software. Over the past 6 decades, the cost of computer memory has halved every 2 years, leading to a reduction in the cost of hard drives by more than 100 million times, and of fast access memory by 10 trillion times. If such savings were applied to all our purchases, you'd be able to buy all the real estate in New York for less than 10 cents, and all the gold mined in the world for $1. Each of us has personal memories somehow connected to this impressive improvement in information storage technology. I vividly remember working at a bakery during high school to save up for a computer with just 16 kilobytes of memory. When my classmate Magnus Bowden and I wrote and successfully sold a text editor for this computer, we had to fit it with an ultra-short code so there would be some space left for the text itself to be edited. Having gotten used to a 70 kilobyte floppy disk, I was amazed by the advent of the smaller 3.5-inch floppy disk with a whole 1.44 megabytes. It could fit an entire book, and then my first hard drive with 100 megabytes, which today would barely be enough to download a single song. It seems utterly impossible to reconcile these youthful memories with others. Later on, many years later, I bought a hard drive with 300,000 times more capacity for $100. Is there anything in these memory devices that evolved naturally rather than being created by humans? Biologists are still investigating how the first living organisms passed on information to subsequent generations, assuming that these mechanisms were quite primitive. Philip Hollinger's team at the University of Cambridge succeeded in synthesizing an RNA molecule capable of encoding 412 bits of genetic information and creating RNA chains longer than itself. This discovery confirmed the hypothesis of the RNA world, according to which the first forms of terrestrial life were short self-replicating RNA chains. Among the memory carriers known to us today that arose through natural evolution, the genome of the bacterium Candidus carcinella rudi is one of the most compact, storing up to 40 kilobytes of information. In comparison, the human genome holds about 1.6 gigabytes, roughly the same as a movie downloaded from the internet. The yeast genome contains 12 megabytes, the fruit fly's genome 175 megabytes, the rice genome is about 430 megabytes, and the chicken's is 1 gigabyte. There are also creatures with genomes larger than that of humans. For example, the corn genes encode 2.3 gigabytes, and the dog's genome is 2.4 gigabytes. These examples illustrate the vast diversity in genome sizes, reflecting the complexity and variability of life forms, from microorganisms to plants and animals. Your brain can store much more information than your genome. Electrically, it's about 10 gigabytes based on the activity of 100 billion neurons, or biochemically, about 100 terabytes, based on the degree of connectivity of neurons in synapses. Comparing these volumes with computer memory shows that modern machines already surpass any biological systems in terms of information storage capacity, and they do so with continually decreasing costs. The memory mechanism in our brain works completely differently from computer memory, not only in its structure, but also how it is used. Accessing information on a computer or hard drive requires knowing the exact location of the data, whereas retrieving information from the brain only requires a rough idea of what you're looking for. In a computer, each set of bits has its own unique address, and you need to specify this address, similar to how you would search for a book in a library. In contrast, to find information in the brain, it's enough to recall keywords or related images, and the necessary data pops up in our mind. This process is similar to how search engines work on the internet, where you just need to enter a query to get the desired result. This type of memory is called associative because the search of information occurs through associations, not a fixed address. In a famous 1982 paper, physicist John Hopfield presented a model demonstrating how a network of interconnected neurons could function as associative memory. This idea is still widely cited because it applies to any physical system with multiple stable states. For example, imagine a ball that can settle into one of two depressions on a surface. And if you place the ball close to one of these points, it will independently roll into the nearest depression. Hopfield showed that a complexly organized network of neurons creates a similar landscape with many potential minima where the system can settle. And it was later established that each 1,000 neurons could encode 138 different memories without significant confusion between them. We've already learned that physical objects can store data. But how do they perform computations? Computation is the process of changing the state of a data storage. In other words, to perform computations, information is transformed through a procedure that mathematicians call a function. You can think of a function as a device for processing information. Similar to a meat grinder, you input raw data from the top, turn the handle, and as a result, you get processed data. This process can be repeated multiple times, each time yielding a new result. However, the data processing itself is completely predetermined, meaning it is deterministic in the sense that with the same input, you will always get the same output. Every computation transforms incoming information by performing a mathematical operation on it. This is the essence of a function, and although such a definition may seem overly simplified, it works very well in practice. There are simple functions, for example, the not function, which takes one bit as input and changes it to the opposite, turning 0 into 1 and vice versa. The functions we encounter in school mathematics usually correspond to the buttons on a calculator, taking one or more numbers as input but always returning one number. For example, the squaring function returns a number multiplied by itself. Thus, in this illustration, the function f takes a sequence of bits representing the number 5 as input, and as a result, it outputs its square, 25. There are also very complex functions. If you have a function g that takes the placement of chess pieces as input and returns the best next move, you could win a computer world chess championship. If you have a function that takes the state of all financial markets as input and suggests stocks to buy on output, then you could quickly become wealthy. Many researchers in the field of artificial intelligence see their goal as developing ways to compute certain functions for any initial data. For example, the goal of machine translation is to transform a sequence of bits representing text in one language into another sequence of bits reflecting the same text in another language. The goal of creating automatic video recognition systems is to transform a sequence of bits encoding a video into a sequence of bits describing that very video in words. Thus, the function h transforms a sequence of bits representing a video into the corresponding textual description, a cat. In other words, the ability to compute complex functions enables the creation of an intelligent machine capable of achieving complex goals. This helps us better understand how matter can possess intelligence. That is, how organized fragments of matter are capable of processing complex functions. In this context, we are not interested in the static preservation of information, as in the case of an inscription on a watch, but in a dynamic state capable of complex and controlled changes, evolving from the present to the future. The structure of atoms in such a system must be more organized than in solids, where processes are generally uninteresting, but not as chaotic as in liquids or gases. Ideally, the system should take the given initial conditions as a starting point and independently evolve to a state that can be interpreted as the solution to a problem. In such a case, we can say that the system has computed our function. A good example of this approach could be the creation of a simple yet significant system from unintelligent matter that performs the NAND function, known as the NAND gate. NAND is an abbreviation for not and AND. An AND gate outputs 1 only if there are 2 ones on its input. NAND does precisely the opposite. This system takes 2 input bits and outputs 1 bit. The result is 0 if both input bits are 1, and the result is 1 in all other cases. The NAND logic gate computes a third bit C based on 2 input bits A and B, with the rule C equals 0 if A equals B equals 1 and C equals 1 in any other case, and then sends the bit C value as output. The NAND gate can be utilized using many different physical devices. One could construct such a system with 2 switches that complete a circuit with an electromagnet, which activates only when both switches are closed, in the on position. For instance, in this electrical circuit, keys A and B correspond to input bits with values 0 when open and 1 when closed. When both are closed, the current through the electromagnet opens the key C. Another switch can be placed under the electromagnet, which the electromagnet will open upon activation. Interpreting the 2 first switches as input bits and the third as the output bit, we obtain a NAND logic element. In it, the third switch opens only when both the first 2 are closed. There are also more practical ways to create a NAND element, such as using transistors. For example, in a circuit, bits correspond to potential values, 0 when the potential is 0, and 1 when the potential is 5 volts. When voltage is applied to the bases of both transistors, A and B, the potential at point C drops almost to 0. Notably, in modern computers, NAND elements are usually integrated into chips or other components made from silicon crystals. In computer science, there exists a theorem stating that the NAND logic element has universal computational capabilities. Thus, if you have enough NAND gates, you can assemble a device capable of computing anything. The universality of the NAND gate means that the computation of any well-defined function can be achieved by interconnecting NAND gates. By well-defined function, we refer to what computer scientists and mathematicians call a computable function. That is, one that a computer can theoretically handle given infinite resources of time and memory. However, Alan Turing and Alonzo Church proved that there are functions which, although describable, cannot be computed. Therefore, if you have enough NAND elements, you are capable of creating a mechanism that can compute any task. To see how this works, consider the following diagram. It shows the process of multiplying numbers using only NAND elements. For example, modules performing addition and multiplication operations take 2 binary numbers as input, each encoded with 4 bits, and output a binary number represented by 5 bits in the case of addition and 8 bits in the case of multiplication. Scientists from MIT, Norman Margolis and Tommaso Toffoli, introduced the term computronium to denote any substance capable of performing computations. As we see, creating computronium is not too complicated. It simply requires the ability to interconnect NAT elements in any necessary configuration. And of course, there are many other forms of computronium. For instance, neural networks can also perform any computation and are thus another form of computronium. Scientist and entrepreneur Stephen Wolfram demonstrated that a similar assertion is true for simple systems such as cellular automata, which adjust the state of each bit depending on the states of its neighboring bits. And in 1936, Alan Turing, in his seminal paper, proved that a simple computational machine, now known as Turing's universal computer, can also perform any computation. Thus, matter has the potential to perform any precisely defined computation in a variety of ways. But that's not all. Alan Turing established something even more fundamental. If a computer can perform even a very basic set of operations, it possesses universality. This means that, given sufficient resources, it can perform any actions that any other computer is capable of. Turing proved the universality of the Turing machine, and by bringing it into the physical world, we have just demonstrated how diverse the category of universal computing devices can be. Moreover, Stephen Wolfram stated that the most complex physical systems, from chaotic and variable weather to the contemplative brain, become a universal computer if allowed to change their size without temporal constraints. This very fact, that is, again, the fundamental possibility of performing identical computations on any universal computer, means that computation does not depend on the physical substrate carrier to the same extent as it does not depend on information. Computation, like information, exists independently as it lives its own life. For example, if you were a character in a future computer game with full consciousness, you would never be able to determine the operating system within which you function. That is, whether you were created on a workstation running Windows or on a smartphone with Android, since you do not depend on the physical carrier. You would also have no way to know which specific transistors are used in your company's microprocessor. This inevitably recalls the trilogy The Matrix, which shows an example of substrate independence. In this story, people live in a virtual reality, unaware of their true physical existence in a world controlled by machines. The film raises the question of whether the physical substrate of consciousness matters if the experience inside the matrix is indistinguishable from reality. Thus, the characters in the film are capable of experiencing emotions, memories, and sensations, being completely detached from their biological bodies. But we are not here to dissect the film, so let's talk about physics instead. Fundamental substrate independence manifests in numerous vivid examples from physics. For instance, waves have various characteristics, such as speed, wavelength, frequency, and physicists can solve equations related to them without delving into the details of substrate interaction. When you hear a sound, you perceive sound waves spreading in the air, and we can calculate many aspects of these waves, from their decreasing intensity with distance to their passage through a door or reflection from walls, without knowing the composition of the air. In fact, we do not even need to know the molecular composition of the air, because the only thing important for the famous wave equation is the speed of sound, which is easy to measure and is approximately 300 meters per second. This example with the wave equation gives us three important insights. First, independence from the substrate does not mean complete independence from matter, but rather indicates that many details of its structure do not matter. You won't hear sound in a vacuum, but replacing air with another gas won't significantly change the perception of sound. Similarly, you cannot perform computations without a material carrier, but any matter will do if it can be organized into NAND elements, a neural network, or other basic components of a universal computer. Second, substrate-independent phenomena live their own life. Whatever the substrate may be, a wave can travel across the surface of a lake, although water molecules only move vertically up and down, similar to spectators at a stadium creating a wave. Third, often we are interested in aspects of a phenomenon that are not tied to its physical carrier. A surfer, for instance, cares about the height and condition of the wave, not its molecular composition. The same is true for information as it is for computations. When two programmers are looking for a bug in code, they are unlikely to discuss the characteristics of transistors. Thus, we have come close to a possible explanation of our initial question about how crude physical matter can give rise to something as immaterial and abstract as mind and consciousness. The mind seems immaterial to us, thanks to its ability to exist independently of the material carrier. In essence, computation is a specific organization of atoms in space and time, and what matters is not the composition of matter, but this organization itself. Matter in this context does not play a key role. That is, matter serves as hardware, while organization serves as software. The independence of computations from the substrate proves that artificial intelligence is possible. Intelligence does not require flesh, blood, or carbon atoms. This property of independence from the substrate allows engineers to continuously replace one technology in computers with another, more advanced one without needing to change the software. This phenomenon is well illustrated by the history of data storage technology development. The cost of computational operations halves approximately every 2 years, and this trend has been consistent for over a century, leading to the reduction in the cost of computers by an astronomical factor of 10 to the 18th power, or a million times. Here is the chart. It shows how, since 1900, the purchasing power of $1,000 in terms of computational power, measured in flops, floating point operations per second, has grown. Simple computation operations, such as changing a bit or activating a NAND gate, form the basis for assessing this power. If the same price reduction had occurred with all goods and services, 1/100th of a cent would allow you to purchase everything produced on Earth in a year. This dramatic reduction explains why computational processes have penetrated all areas of our lives today, moving from separate buildings occupied by computing machines to our homes, cars, and pockets. Applications have been found in the most unexpected places. For example, 15 years ago, I played soccer, and even then, the cleats had a special compartment for a chip. Its main function was to house a sensor to collect data about the player's movements and other parameters during a match or training. Today, smart footwear is commonplace, and we are more likely to discuss refrigerators with artificial intelligence functions. Yes, they already exist. But why does our technological progress continue to demonstrate the same regularity in doubling performance, following a trajectory that mathematicians define as exponential growth? The reason lies not only in the reduction of transistor sizes, according to Moore's law, but also in the overall development of computing technologies, as well as many other areas, from genome sequencing to brain tomography. This process is described by Ray Kurzweil as the law of accelerating returns. In nature, we see a similar pattern of regular doubling, caused by each new stage building on the results of the previous one. An example of such exponential growth is the development of an embryo after conception, when the number of cells doubles every day. Similarly, according to the theory of inflation, our universe expanded exponentially at the beginning of its existence, doubling its size at equal intervals of time. In the field of technology, we see the same thing. The advancements of one generation of technology serve as the basis for the development of the next generation, which is twice as powerful as the previous one, contributing to a cycle of constant doubling. However, there are concerns that this doubling trend may be approaching its limit. Although the miniaturization of transistors is already encountering physical limitations, Ray Kurzweil asserts that Moore's law is just a specific case of a broader pattern of progress. Ray points out that Moore's law is the manifestation of not the first, but the fifth technological paradigm, transferring exponential growth to the realm of computing technologies. Each time the limit of one technology is reached, it is replaced by the next, more advanced one, allowing the exponential growth to be sustained. For example, the replacement of vacuum tubes with semiconductor transistors and then with integrated circuits shows how we move to new generations of technologies when previous ones reach their limits. Despite uncertainty about which new technology will come to the forefront, one thing is clear: we are still far from reaching the fundamental limits set by physical laws on the ability of matter to compute. Research by Seth Lloyd of the Massachusetts Institute of Technology points to this limit, which exceeds current capabilities by 33 orders of magnitude. If the trend of doubling computer performance every few years continues, reaching this limit will take more than 200 years. While all universal computers are capable of performing the same computational operations, some stand out for their increased efficiency. For instance, millions of multiplications do not require millions of different devices, each performing multiplication with individual transistors. Only one device is needed, capable of being used repeatedly with proper management of data flow. Following this principle of increasing efficiency, most modern computers are designed so that any computation is divided into a series of steps, between which data moves from computational modules to memory modules and back. This approach to computer architecture was established in the mid-20th century by pioneers of computer science including Alan Turing, Konrad Zuse, Presper Eckert, John Moschly, and of course, John van Neumann. A distinctive feature of this architecture is the storage in memory, not only user data, but also the software that regulates data processing. The central processor at each stage determines which operations should be performed with the data. A separate memory element, called the command counter, tracks the order of operations, automatically moving to the next command. Modern computers are able to accelerate the computation process by parallel data processing, reusing the same computational blocks. If a task can be divided into independent parts, they can be processed simultaneously on different devices. The parallelism of computations is particularly evident in quantum computers. Theoretical physicist David Deutsch, one of the pioneers of quantum computing, states that a quantum computer distributes the information available to it across countless copies of itself throughout the multiverse, allowing it to solve problems incredibly fast. Although the commercial realization of quantum computers has not yet been achieved, hundreds of millions of dollars are invested in them because they promise a revolution in such areas as encryption and neural network training and can effectively model quantum mechanical systems, including atoms, molecules, and new compounds, replacing traditional experiments in chemistry laboratories. Although even the simplest calculator outpaces me in the speed of arithmetic calculations, it will never improve its performance, no matter how much it practices. A calculator is incapable of learning. Every time it executes the square root function, it repeats the same actions without change. Similarly, the computer chess program Stockfish, which you can play against, lacks the ability to analyze its mistakes and improve. It always follows a predetermined evaluation function developed by programmers. In contrast, Magnus Carlsen, after losing his first chess game at the age of 5, began a learning process that led him to become a world champion 18 years later. The ability to learn is a key characteristic of advanced intelligence. We've seen how a piece of inanimate matter can store data and perform calculations. But how can it learn? Solving complex problems requires performing specific functions. And matter, organized in a certain way, can compute any computable function. We have long known how to organize matter to create calculators and chess programs. Now, the challenge is to allow this matter to reorganize and improve itself independently. To clarify the mechanism of learning, let's consider a simple physical system capable of learning to compute the sequence of digits in the number pi, or any other number. We've already discussed using a surface with depressions between hills as a data storage medium. If we imagine that this surface is made of soft clay and constantly impact it to create depressions corresponding to the sequence of digits in pi, the clay would remember these numbers. Thus, the clay has learned to compute significant digits of pi. Other physical systems, including the human brain, are capable of learning much more efficiently. Scientist and inventor John Hopfield showed that his network of intersecting neurons could adapt and memorize certain states if it was systematically brought into these states. Similarly, you remember your family members well because you see them often. Modern neural networks have transformed not only biological but also artificial intelligence, particularly in the field of machine learning, which studies algorithms that improve through experience. Before delving deeper into their learning mechanisms, it's essential to understand how exactly they perform computations. A neural network consists of interconnected neurons that influence each other. The brain contains hundreds of billions of neurons, each connected to thousands of others through synapses. And these synaptic connections encode most of the information in your brain. Neural networks can perform functions similarly to networks made of NAND logic gates. For example, neural networks that receive input data on the brightness of image pixels can output possibilities of a certain person's presence in these images. Each artificial neuron processes the data received from the previous layer, performs a calculation of the weighted sum, applies a simple function, and then passes the result to the next layer, gradually increasing the level of detail in the processing. A typical face recognition neural network may include hundreds of thousands of neurons. Neural networks are often depicted as diagrams with points representing neurons and lines symbolizing the synapses connecting them. In the brain, synapses are complex electrochemical structures that include various components such as axons and dendrites, and there are many types of neurons with diverse functions. The precise mechanics of how neurons interact with each other remain a subject of research by neurobiologists. Nevertheless, it is already known that artificial neural networks are capable of performing the most complex tasks at the level of human intelligence. In modern models of artificial neural networks, the state of each neuron is represented by a single number, and the strength of each synapse is also represented by a number. During operation, each neuron updates its state based on information from neighboring neurons, taking into account the weight of synaptic connections. Sometimes a constant is added to the result, after which an activation function is applied, determining the new state of the neuron in the next cycle. The simplest method of using a neural network as a function is to make it straightforward, turning it into a transmission channel where information is sent only one way, loading the top layer of neurons from the input of the function and reading the output from the layer of neurons below. The effectiveness of such a neural network structure emphasizes the universality and insensitivity to the details of its construction. In 1989, George Sabentko, Kurt Hornick, Maxwell Stinchcomb, and Halbert White proved that even simple neural networks possess universality. That is, they are capable of computing any function with a given accuracy simply by adjusting the values of the weights of sympathetic connections. This suggests that the complexity of biological neurons arose not from necessity, but from a drive to increase efficiency, as evolution, unlike human engineers, does not get rewarded for simplicity and clarity of proposed designs. It is truly astonishing. How can such simple mechanisms perform tasks of arbitrary complexity? For example, how is it possible to perform multiplication when you only have the ability to create weighted averages and apply a single specific function? If you're curious about how this works, here's an illustration from Life 3.0, showing how 5 neurons can multiply 2 numbers, and 1 neuron can multiply 3 bits. Max Tegmark writes, "Although you can prove theoretical possibility of computing anything with a sufficiently large neural network, your proof says nothing about whether it can be done in practice with a network of reasonable size. Indeed, the more I thought about it, the more I was amazed that neural networks actually work so well." Imagine you are tasked with classifying black and white photographs of megapixel resolution, dividing them, for example, into categories of cats and dogs. Given that each of the million pixels can have one of 256 possible values, the total number of possible images reaches 256 to the power of 1,000,000, and the corresponding function, which links images to probabilities, is defined by a list of 256 to the power of 1,000,000 elements, exceeding the number of atoms in the known universe. Nevertheless, neural networks with thousands and millions of parameters manage these tasks with surprising efficiency. But how? How can neural networks be so economical, requiring such insufficient number of parameters for their operation? After all, one can prove that a neural network compact enough to fit within our universe would spectacularly fail to approximate almost all functions, succeeding only in a laughably tiny part of all computational tasks one might expect from it. Max Tegmark, together with Henry Lin and David Rolnick, wrote an article in which they came to a surprising conclusion. The question of why neural networks work so well cannot be resolved only by methods of mathematics, because a significant part of this solution relates to physics. We discovered that the class of functions introduced to us by the laws of physics, which indeed made us interested in computing, is an incredibly narrow class of functions, because for reasons we do not fully understand, The laws of physics are amazingly simple. Moreover, the tiny part of functions that neural networks can compute is very similar to the tiny part that physics makes us interested in. We also continued previous work showing that deep learning neural networks are much more efficient than shallow ones for many of these interesting functions. A simple task of multiplying n numbers requires a colossal 2n neurons for a single layer network, and only about 4n neurons in a deep network. This helps explain not only the increased enthusiasm among AI researchers for neural networks, but also why evolution needed neural networks in our brains. If a brain capable of predicting the future provides an evolutionary advantage, it must develop a computational architecture suitable for solving precisely those computational tasks that arise in the physical world. Now that we have understood the principles of how neural networks operate, let's return to the question of how they can learn, and how are they able to improve their computational abilities merely by updating the state of their synapses. Canadian psychologist Donald Hebb, in his foundational work of 1949, titled The Organization of Behavior, asserted that the synaptic connection between two neurons that frequently activate together becomes stronger over time. This means their synaptic connection gradually intensifies, teaching them to activate each other. This idea has been popularly expressed as cells that fire together, wire together. Although we are far from fully understanding the mechanisms of learning in the human brain, even these fundamental principles can explain how learning occurs in neural networks in a number of interesting cases. John Hopfield provided an example of using Hebb's rule, which allowed his simple artificial neural network to retain complex memories through the repetition of the process. This method of exposing information for training is often referred to as training the neural network. In modern AI systems based on artificial neural networks, Hebb's rule is often replaced by more complex techniques, such as the method of backpropagation of errors or stochastic gradient descent. However, the basic principle remains unchanged. There is a simple deterministic rule, similar to a law of physics, according to which synapses are updated over time. Surprisingly, by following this simple rule and using extensive databases during training, a neural network can be taught to perform extremely complex computations. Most digital computers increase their efficiency by decomposing a task into many steps, reusing the same computational modules. Artificial and biological neural networks operate similarly. In your brain, there are areas that represent what in computer science is called recurrent neural networks. Information in them can circulate in various directions, allowing what was previously an output to become an input at a later stage. This distinguishes them from feed-forward signal networks. The network of logic gates in a computer processor is also recurrent in this sense. It continues to work with already processed information, while simultaneously accepting new data from the keyboard, touchpad, camera, etc. These data can also influence current computations, determining how new data will be output to the screen, speakers, printer, or via wireless network. Similarly, a neural network in your brain is recurrent because it receives information from the eyes, ears, and other sensory organs, allowing this information to influence current computations, which in turn determine how your muscles and body will move. The history of learning is as ancient as life itself, as every self-replicating organism is engaged in copying and processing information, implying some level of learning. In the era that might be called Life 1.0, organisms did not have the ability to learn during their individual lifetimes. Their reactions and information processing were encoded in the DNA inherited from ancestors, so the learning process was slow and occurred at the species level through evolution from one generation to the next. About 500 million years ago, animals with neural networks appeared on Earth, providing them the ability to adapt and learn based on personal experience during their lifetimes. The emergence of Life 2.0 marked an evolutionary success as these creatures were able to learn quickly and spread across the planet. Over time, the ability to learn in life improved at an increasing rate. One species of primates managed to adapt so well to learning that they learned to use tools, developed the ability to speak, and began to build societies that spread around the world. This society itself became a system capable of remembering, computing, and learning, doing all this at an ever-increasing speed as each new invention generated the next, from the invention of writing to the advent of the internet, From the discovery of fire to electricity, from Galileo's telescope to the launch of the James Webb Space Telescope, from Mendel's law of inheritance to CRISPR-Cas9 and genome editing. What will the future historians add to this list of innovations accelerating the learning process? The answer is apparent: artificial intelligence. Philosophers have pondered the mystery of consciousness for millennia, but the advent of artificial intelligence has suddenly made this question particularly relevant. Should artificial minds be granted rights? Does the conferment of rights directly depend on AI's ability to exhibit conscious behavior and experience emotions such as suffering or joy? Some people want their robots to be insensible, so they do not feel guilty about owning a conscious being. Conversely, others might want to transfer their consciousness into a computer, freeing themselves from biological constraints. But how important is the awareness for the long-term prospect of life in space? If technological advances allow intelligent life to thrive in the universe for billions of years, how can we be sure that this life will remain conscious and be able to consciously perceive what is happening? Otherwise, might everything turn into the very play that physicist Erwin Schrödinger described? Played before empty rows of seats, it exists for no one, and wouldn't be more correct to speak of it as non-existent. Debates on consciousness often generate more emotions than rational conclusions, due to participants' inability to understand each other due to differing definitions of consciousness. Max Tegmark uses a broad definition. It encompasses all existing definitions and is not limited to biological forms. Consciousness is subjective experience. This means that if you experience any feelings, you have consciousness. This definition does not mention behavior, perception, self-awareness, emotions, or attention. According to this definition, a person is conscious even in sleep. Similarly, any system that experiences pain is considered conscious, even if it cannot move. This approach leaves open the possibility of consciousness in artificial systems, even if they exhibit only as software without a physical body. It also emphasizes the impossibility of circumventing consciousness through attention. Yuval Harari, in his book Homo Deus, A Brief History of Tomorrow, argues that if a scientist claims that references to subjective experiences are inappropriate in science, he must also prove the inadmissibility of torture or violence without referring to subjective experiences. Without such a reference, each of us is seen as a collection of elementary particles moving according to the laws of physics, and then it's unclear how any actions can be impermissible. One of the most diligent researchers on the topic of consciousness is philosopher David Chalmers. With his perpetual smile and leather jacket, he gathered data on more than 20,000 works dedicated to the topic of consciousness and concluded that no other field has seen so many scientists produce so little consensus, that is, universally accepted statements. Chalmers identifies two mysteries associated with the workings of the human mind. The first concerns the brain's information processing, which he calls the easy problem. How does the brain perceive signals from the senses, use language to communicate about its internal state, remember, compute, and learn? These issues are complex, but they relate to intellect, not consciousness. In the field of artificial intelligence, information processing is rapidly progressing, and we see clear successes in data-rich tasks such as driving cars, recognizing images, and understanding statements made using natural language. The second mystery, the hard problem of consciousness, involves subjective experiences. For example, a human driver reacts to the world around them and experiences emotions. Meanwhile, an autonomous vehicle, processing information from sensors, feels nothing and performs its task excellently. David Chalmers wonders why a particular organization of matter leads to the emergence of consciousness, given that the same elementary particles underpin everything. To answer this question, we should start by acknowledging a solid fact. Some conglomerates of particles feel conscious, while others do not. This leads us to three key questions. 1. What physical features distinguish conscious systems from non-conscious ones? 2. How do physical properties determine the quality of sensations, such as perception of color or the feeling of pain? 3. Why do some clusters of matter become conscious while others do not? Computer scientist Scott Aaronson A former MIT employee humorously referred to the first of these key questions as the pretty hard problem, following David Chalmers' example. Additionally, the other two questions were called the even harder problem and the truly hard problem. It is important to acknowledge the potential for creating a scientific theory that addresses questions about consciousness. A theory predicting which systems possess consciousness is scientific if it can identify which processes in the brain occur consciously. Imagine a theory that could determine the presence of consciousness in any physical system. For instance, if we could connect a brain to a device that reads information in real time, it could confirm or refute the theory. If the theory predicted conscious experiences that were not corroborated by observations, it would be disproven. The possibility of its refutation makes such a theory scientific because it is subject to testing and falsification. Some of you may now be skeptical and think, what nonsense! There's no proof that anyone actually realizes anything, even if they claim to be conscious. However, this objection does not make the theory of consciousness unscientific, as the possibility of testing the theory remains because you can switch places with the skeptics and check their own experiences. However, the testability becomes less clear for more complex questions, such as predicting subjective color perception. In contemplating the limits of scientific knowledge, it is important to remember that these boundaries change over time. 4 centuries ago, Galileo Galilei, impressed by the capabilities of physics based on mathematics, compared nature to a book written in the language of mathematics. He could precisely predict the trajectories of falling objects, but did not know why they had color or texture. These aspects were beyond the scope of science. However, this did not mean they would remain forever unknowable. With the discovery of Maxwell's equations and the Schrödinger equation, it became possible to mathematically describe light, color, and the physical properties of substances. Scientific and technological progress has expanded the horizons of science since Galileo's time, ranging from studying subatomic particles to black holes and exploring a universe that turns out to be 13.8 billion years old. This leads to the question of what areas of knowledge still remain beyond scientific understanding. For Max Tegmark, consciousness is just such an unresolved issue. But one thing can be said for certain. If we do not attempt to explore consciousness, no progress will be made. Discussing the consciousness of artificial intelligence leads us to the even harder problem. What could the subjective experiences of a conscious AI be like? Currently, scientists lack a theory that could fully answer this question, and it is even unclear whether such an answer is feasible. It is akin to trying to explain someone born blind what the color green looks like. Nonetheless, we can make assumptions about some aspects of silicon consciousness. For instance, AI might have a far broader spectrum of perceptions than humans due to having more types of sensors and feedback loops. Therefore, we should not assume that AI perceives the world in the same way humans do. Moreover, an artificial intelligence, packed in a volume comparable to the human brain, can process information much faster because electromagnetic signals travel at the speed of light, millions of times faster than the signals travel through neurons. However, the larger the AI, the slower it calculates, due to the time required for signals to travel between its parts. For example, an AI the size of Earth might experience about 10 conscious moments per second, similar to a human, while an artificial intelligence the size of the Milky Way might experience 1 conscious moment every 100,000 years. Large AIs can delegate most of their computations to smaller subsystems for more efficient operation, just as the human brain delegates some automatic functions and reflexes to unconscious processes. This raises the question of whether parts of a conscious entity can also possess consciousness. According to the integrated information theory, in an astronomically large artificial intelligence, consciousness may be present, but much of its information processing will be unconscious. If this is the case, then the process of merging smaller AIs into a single collective mind, their individual consciousness would disappear. If the theory is incorrect, the collective mind could exist alongside many conscious smaller minds, creating a hierarchy of consciousness from microscopic to cosmic scale. Analogous to the human brain, where unconscious information processing, System 1, according to Kahneman, involves easy and automatic thinking processes. it can be presumed that artificial intelligence would also perform similar tasks unconsciously. Labor-intensive and slow processes that require effort and control, System 2, would be conscious. In summary, if theory providing a solution to the pretty hard problem of consciousness passes strict experimental tests, it would significantly narrow down the possible ways an artificial intelligence could experience consciousness. An intriguing question arises about the subjective experiences of future AI. Some aspects of our consciousness are linked to basic survival and reproduction instincts, but AI may lack the qualia such as hunger or fear. If AI aimed at achieving complex goals, it might exhibit a drive for self-preservation. In a community of similar systems, artificial intelligence would not need human fear of death, thanks to the ability to create backups. By making regular backups, the most AI could lose is the memory content accumulated since the last backup. Therefore, artificial intelligence might be indifferent to the human sense of individuality, as it can easily share information and skills with other AIs, leading to the emergence of a collective consciousness. This scenario was explored in the film Her by Spike Jonze. From a physics standpoint, everything that future life, from machines to new life forms, might aspire to create is merely particularly arranged elementary particles. But if all life is an agent of entropy that organizes matter, where will a super-advanced conscious AI draw energy? Future life, having reached its technical limits, will be able to rearrange particles much faster and more efficiently, initially using its computational power to find the most efficient methods, and then following these methods, rely on available energy sources to achieve the desired particle organization. We've seen how matter can be turned into a computer, and how it can be turned into energy, so this is the only fundamental resource required. Once future life reaches physical limits and hits them, it has only one resource for growth: more matter, and the only way to do that is to expand into the universe, into the depths of space.